All right, sorry, jumped ahead. All right, everybody hear me okay?
Yep.
I'm good. All right, cool. All right, so thanks, Jeremy. Okay, somebody turned me off and on again. All right, so we're going to take a look at the Storm-Relative Velocity Enhancement, the SRVE Airstream again. Those of you who have been around the High Plains Conference have heard me talk about this before, and if you're in the Weather Service, Aaron and I have presented on this topic before at the in the guest speaker series. So one of the things we're going to take a look at here is when the enhancement doesn't look like an enhancement, essentially. It looks more like a minimum. So I'll kind of go through that here in just a second. All right, so what is a SRVE, or a Storm-Relative Velocity Enhancement? This is a look at a case from Mayfield, Kentucky EF3. It's a case where the radar is located north of the storm, and the SRVE shows up as an asymmetric signature originating from the forward flank portion of the storm. It's related to the precipitation downdraft and oriented on the backside of the low-level mesocyclone. And I should say this is with supercells we'll be talking about here. So in the 88D, you see this as a low-level storm-relative velocity enhancement. And of course, like most 88D features, best seen inside 40 nautical miles from the radar or below about 1 kilometer. And again, what we'll get into today is more about this, but it could be viewed as an inbound or an outbound signature, depending upon where you are. But it may not be seen in this orientation at all if the SRVE is perpendicular to the radar beam. But we're going to throw you for a loop here just to start. A little bit of a name change going from the Storm-Relative Velocity Enhancement to the Left Flank Velocity Enhancement. Plot twist. So again, we'll talk about why the name changed, but this is really the area of the storm we're looking at. The black outline kind of shows the 40 to 50 dBz reflectivity outline of the storm. So again, we're looking at this portion that's originating from deeper within the forward flank region here, showing up as green colored into the hook echo region. So the left flank velocity enhancement, again, it's an airstream that originates in the forward flank there. But what we've found is that it aligns closely with the left flank convergence boundary, which was identified by Beck and Weiss and has been talked about by many others in the meantime since 2013. So really, we decided to by we, I say Aaron and I kind of looked at this and talking with Bruce Lee up at UND, kind of decided maybe the best thing to do is to orient it more closely to where it's originating from. So the name change allows for more of a consistent naming convention with peer-reviewed research. And there's that area of left flank velocity enhancement. But obviously with the 88D, it's going to be tough to see any kind of convergence boundary really well because of the different viewing angles, of course, and then, of course, the height of the radar beam itself. So instead, the resultant airstream is more likely to be viewed with the 88D. And we've seen high-resolution modeling showing wind vectors accelerating towards the inflow region under the low-level mesocyclone. So looking at this a little bit further from the Beck and Weiss research, again, you can see in red there the left flank convergent boundary. But the acceleration along with that or in that vicinity region, the airflow in towards the hook echo region and under the low-level mesocyclone is probably more easily seen with the 88D. So again, why is this airstream important? You know, there's there's a multitude of research papers out there that really look at all of these different airstreams and where they originate from. And going even back to the Markowski-Richardson stuff, looking at how the low and mid-level mesocyclone is important for the dynamic lifting of the airstream that eventually makes it into the tornado seed. Let me go back there again. And then the study from Parker and Dahl showing that this is a descending airstream, that which originates from the forward flank region. And this is the airstream that actually makes it into the tornado itself. And then we see that these parcels riding along this airstream are acquiring horizontal vorticity. So again, there's a multitude of studies out there, and here's a look at another one from Schuth et al. 2021. This particular graphic here, just going through all these different individual studies here. Beck and Weiss, again, they modeled low-level boundaries in general, noted that they were mainly looking at the convergence signatures associated with each of the main boundaries, and they followed several of them, but the rear flank gust front formed first, followed by the left flank convergent boundary, and then the forward flank convergent boundary. And the forward flank convergent boundary is important more so with the streamwise vorticity current, or the SVC, which is what Schuth et al. Modeled there. And they found that the SVC aligned along and on the cool side of the forward flank convergent boundary. And you'll see later on here in the presentation why I kind of differentiate between the two here. But what's of note in their studies was that they found that the SVC contributed to mid-level vertical vorticity and not that which made it into the tornado itself, which was also found by Merdzak et al., which noted that the parcels destined for the tornado seed collect along boundaries that are co-located with prominent horizontal buoyancy gradients, which of course in the forward flank region is in existence because of the precipitation downdraft, and then forming rivers of vorticity in the lowest few hundred meters. And that's what actually feeds the, in research studies, the tornado-like vortex or the tornado seed. And so the rivers of vorticity was also looked at with Kofer and Parker back in 2017, noting some of these same areas of horizontal vorticity that were prominent, originating from deeper within the forward flank region. And of course, everyone's probably seen the Lee-Orff simulations, which are, early on really looking at the SVC, streamwise vorticity current, when he modeled the 2011 El Reno EF5. Some awesome work coming out of there that really shows a lot of these boundaries, but just how turbulent the entire inflow region is. But again, found that parcels originating along the forward flank downdraft boundary there, and on the cool side end up in the streamwise vorticity current, which flows into the low-level mesocyclone, which is an ascending airstream, and that's important to understand that part of it. Operationally, we've seen that the SVC may align at times with the ZDR arc in well-defined supercells, but there again, it's kind of a hit and miss at times. But again, what they found, or what they showed, and in conversations with Kathy Finley and Bruce Lee, again, this area which we've defined as the left flank vorticity enhancement really is that airstream that makes it into the tornado itself. So again, here's more research in that area from Rutuno et al. All of these suggesting that this area is adjacent to the horizontal buoyancy gradient that exists because of the precipitation downdraft. So parcels flowing along this area are acquiring baroclinic vorticity. And here's again some more of those. We looked at Parker and Dahl earlier, and then this is another example from Dahl back in 2014. So again, just kind of walking through all this, parcels acquire baroclinically generated vorticity as they move kind of rearward in a storm relative sense from the forward flank region. As they turn southward into the more of the hook echo region, they briefly ascend before rapidly descending within the outflow. This southward pointing baroclinic vorticity generation really causes, and actually a lot of the research has shown that this is initially crosswise, which allows the vorticity vector to be tipped off of the trajectory and to be kind of tipped upward to eventually be reoriented as vertical vorticity. And then, of course, this vertical vorticity is tilted and stretched upward as it becomes convergence and acquiring under the low-level mesocyclone. That's, of course, because of the upward directed vertical pressure gradient force. So here's a little cartoon I kind of put together with the help of Aaron here, just kind of showing a lot of these boundaries. And then in yellow here is kind of the left flank velocity enhancement, formerly called the SRVE there. But what we notice in a lot of cases in tornadic supercells is that this convergence signature really shows up to exist under the low-level mesocyclone. So what becomes a problem is when this left flank velocity enhancement tends to be not oriented favorably according to where your radar is. So in this particular case, looking again at this figure from Beck and Weiss, if the radar is located, say, east of where the storm is, the left flank convergent boundaries, again, likely not going to be seen with the 88D, but the resultant inflow towards that low-level mesocyclone also will likely not be seen because of it being perpendicular to the radar beam. So in this particular case, it may be hard to define where that is, and so knowing the conceptual model becomes even more important. And again, this left flank velocity enhancement is radar viewing angle dependent. So here's an example from the Bibb Shelby County, Alabama tornado back on 25 March of this year, and this was an EF3 tornado that was responsible for 5 injuries and had a path length of over 50 miles in this particular time frame. So we're going to take a look first at just prior to the tornado touchdown time. Now, of course, this was a high-risk day, so lots of tornadoes reported on this day. Very obvious supercell located to the west-southwest of the radar KBMX here, if you can see that. And this is about 7 minutes before the time of the tornado according to the storm survey anyway, but there were tornadoes reported earlier. So we have the low to mid-level mesocyclone here in the lower right corner. I should say in the upper left is half-degree reflectivity. Upper right is half-degree storm-relative velocity. Bottom right is storm-relative velocity at about 1.8 degrees. And then bottom left is ZDR. So again, the low-level mesocyclone, and I've kind of superimposed that on the lower-level velocity. So you can kind of see where that is. So this area that actually shows up as kind of darker red colors in the upper velocity, storm relative velocity here, which I've outlined with the white line, is kind of where we're looking at. That's kind of that region of the forward flank deeper into the colder air that flows along that particular boundary. So again, it kind of lines up pretty well with where that left flank convergent boundary is, and then of course the resultant airstream, which is going to be more likely to be seen with the 88D. But still in this case, it's going to be perpendicular to the radar beam. And so this is just kind of superimposing that conceptual model on top of a closer look at the storm relative velocity in the low levels. And again, the green outline shows the reflectivity. And I've outlined what I would call the SVC in this particular case, which is really dominating the velocity signal in an outbound sense here because it is oriented more favorably. And again, the left flank velocity enhancement, not so much. And there's the radar beam. We're going to kind of try to cruise a little faster here. I apologize for taking up so much time. It's kind of hard to get all this in here. But so again, understanding the conceptual model is critical because the orientation of the left flank velocity enhancement airstream is going to be perpendicular in this case. So it's going to actually show up as a minimum. There's not much of that velocity signature making it back to the radar to account for that. But instead, what you are seeing in the enhancement in the kind of pink and almost orange colors here is actually related to the SVC, which is an ascending airstream, and not that making it into the tornado. We're going to jump ahead to 1824, and the tornado's ongoing here. But the important point of this is that this is the same supercell tornado on the ground now, but we're located to the northwest of the radar. So again, the low-level mesocyclone, we're actually closer to the radar as well. And again, going back to the research done by Beck and Weiss, here's that left flank convergent boundary, which kind of in an S shape kind of flows almost straight into the low-level mesocyclone, and then you see the rear flank gust front as well. But again, this area right here, now that we're located to the north of the radar, is showing up better as an inbound signature in the green here, kind of highlighted by that white area that I've got flashing there. So again, a closer look at this and oriented toward where the radar beam is. Tornado ongoing here, so that's kind of a given. But notice the airstream, which shows up as an inbound signature, or the green colors here, much more noticeable now that the this particular airstream is oriented more favorably to the radar beam. So again, more velocity signature going back to the radar, returned to the radar is from the left flank velocity enhancement now, this region that kind of flows parallel to that buoyancy gradient. But instead, what you don't see so much of is the SVC. So just a quick comparison there, along with the conceptual model of before the tornado and then after the tornado. And now we're going to step through this individually here, starting from 1736 UTC. So we're a good, I think maybe 17 minutes before tornado time. Jumping ahead 10 minutes here. Well, in black, you should see the outline here of that velocity minimum, or the left flank velocity enhancement region where it should be. But of course, you're not seeing it because it's perpendicular to the radar beam. Jumping ahead another 10 minutes here. Certainly a well-defined storm, and the tornado is actually on the ground at this time. And then as we get closer to the radar, starting to see more of that green color showing up right here. And then as we get closer to north here, even more showing up. And then I've kind of jumped to a different perspective here, but this is to allow you to see that where it is in relationship to the radar, the KBMX radar, of course, and then where that velocity enhancement is showing up related to the reflectivity of the supercell as well. Beam height here at ½ degree is pretty low, down at 6,500 or 650 feet. So we'll zip into some take-home points here. Just this conceptual model that Aaron and I have come up with in the cartoonish form here, I guess, is really based on a whole lot of research trying to identify all of these airstreams, and there are more here, obviously, that I haven't included, such as the left flank momentum surge, which Bruce Lee and Kathy Finley are looking at more at, and then how that relates to the rear flank. But for visualization, some take-home points here quick. Again, it's the left flank velocity enhancement is an asymmetric airstream oriented from the forward flank towards the developing hook echo underneath the low-level mesocyclone. Can be an inbound or an outbound signature. that's only when it's oriented favorably to the radar beam. Of course, when it's not, it can show up as a velocity minimum in this case, which we took a look at from that case that I showed you from Alabama. Again, any of these features and a lot of what Matt Wilson talked about, best seen the closer you are to the radar, with the exception, of course, of the ZDR column. But even still, the height continuity of that allows you to see things in a little bit better sense to correlate them with a conceptual model. The Airstream here is likely descending based on theories associated with tornadogenesis. Of course, you can't realize or visualize that in the 88D because we're seeing 2D snapshots. So a lot of this has to come from inferences from a conceptual model such as this. And then again, case study analysis suggests convergence under the low-level mesocyclone. And this could be a precursor to tornadogenesis. And again, if your radar viewing angle is favorable, you can sometimes see this convergence signature, whereas in cases that don't produce tornadoes, this velocity enhancement tends to blow right past that low-level mesocyclone. So wrapping it all up here, this is more of the gory details of what happens. But again, in red here are all the peer-reviewed research that kind of support this idea of the airstream flowing along the left flank convergent boundary, which is acquiring horizontal vorticity, most likely crosswise, at least initially, as it descends to underneath the low-level mesocyclone. Now that as it makes that turn underneath the low-level mesocyclone, that's where kind of where research suggests that vorticity is getting reoriented into the vertical and becoming streamwise and then stretched, of course, by that low-level mesocyclone vertical pressure, perturbation pressure gradient force oriented upward. Okay, there again is the conceptual model little cartoon I had there. I know I'm kind of past my time, so I'll take any questions at this point.
And everyone's free to unmute themselves now and ask John whatever questions he has. And also, don't worry so much on the time. We have a couple breaks, and since this is virtual, the breaks aren't all that important. So, you know, don't cut yourself off short if you go a little bit over.
Okay, no problem. I didn't want to, you know, short Aaron. He tends to get upset, you know, if I do that.
No, I wouldn't mess with him. No.
I'm already starting to cry.
I realized I kind of, you know, rushed through a lot of this stuff. What I will say is, you know, if you're not familiar with the formerly known SRVE, which is now the left flank velocity enhancement, go back and take a look at some of the work or some of the presentations that Aaron and I have done in the past, either in some of the High Plains Conference things or the Central Region Guest Speaker Series. It's also in on a lot of the documentation that we're doing in TWIP. So I realize it's, you know, it's not an easy concept to grasp. I've been looking at this stuff for well over a decade. So it's a little second nature to me. And of course, it's really kind of a subjective or circumstantial evidence there. But again, the research tends to back up that airstream existing. So it's just a matter of whether we can correlate it with what we're seeing on the 88D.
I'll give a last call for any questions for John. Very interesting topic. Thank you guys, you and both Aaron, for all your work you've been doing. You've simplified it enough now that I can understand it at least, so, or kind of wrap my head around it at least.
Yeah, it's certainly not a simple thing to understand, but that's kind of our goal is to make it useful in the warning operations regime.
Well, all right, I'm going to go ahead and take the presenter role back real quick.
Thanks, I appreciate the time.